it's a pleasure to me introduce the next speaker, Sankhadip. The title of his presentation is Absolute Continuity and Genericity. Thank you.
Thank you, Sandoyo, for the introduction. So, before I talk about genericity or maybe lack of genericity of absolute continuity, I have to define absolute continuity. And before I do that, I would like to talk a little bit about the first example I saw of it. Okay, just to see why we need it. So the example was from Hoff argument. So I won't explain this argument in detail or the premise, but just mention it in passing. So what happens is we want to given a manifold and a dynamical system f m to m. We want to prove it's ergodic, it's this transformation, okay? So what we do, we take any invariant function, say phi, and we need to prove that its value is constant almost everywhere, okay? So phi is so one trick is to notice that the Birkhoff sum, which is say phi tilde, this, and we can define stable and unstable manifolds. We'll assume any structure necessary, okay? So this problem a priori doesn't have any stable and or unstable manifolds, but we'll define them in some way. So the stable manifold WSP is set of all Q such that distance of Fn Q Fn P goes to 0 as n tends to infinity, and unstable manifold is the same with F inverse. It's possible to see that the Birkhoff sum is constant for Birkhoff sum of F, let's denote it by suffix here, of F is constant for WSP. Okay, and similarly, the Birkhoff sum for F inverse is constant for WUP. And if we get an invariant measure, then if we are talking about an invariant measure, then these two functions are equal almost everywhere, okay, from Birkhoff ergodic theorem. Now, what we can do is, suppose we have any 2 points, say point A and point B. Suppose we find a path which is like some stable manifold, then unstable manifold, then stable manifold, then unstable manifold, and it finally reaches B. If everything works out fine, see, this condition holds only almost everywhere, so it's not trivial. Okay, but assuming that everything works fine, then this should imply that phi tilde of A, which is also F or F inverse, doesn't matter, is phi tilde of B. But there's a problem. Like, this scheme is not so easily implemented because of this almost everywhere. This fails, like somewhere there can be a point where this doesn't hold. Okay, so one way to solve this is absolute continuity, which I'm going to define next. AC means absolutely continuous. If I will explain the notation in a minute. Okay. So what is L? L is any leaf. Okay, I will write down the meaning of this notation. L is any leaf and volume of L is the Lebesgue measure on L, and ML is the conditional measure induced So there's a problem with this definition, which is I assume the existence of a conditional measure, which is not so immediate. You need theorems, maybe Rocklin disintegration, which doesn't apply so directly. So for now, I will state this in a different way, which is the following. Any set Y of full volume in M intersects almost every leaf. Sorry, I'll change the notation. in M. Sorry for the inconvenience. So for almost every Z in M, any set Y of full volume in M intersects the leaf L Z. Okay, so what's happening is something like this. Pictorially, this is M, and this is the set Y, which has full measure, and then you have the foliation like this, and this intersection has full Lebesgue measure with respect to the Lebesgue measure of that leaf. Okay. Another terms, again intuitive terms, which is the conditional measure which is being introduced, which is being induced onto the leaves are Lebesgue measures. Okay. So this is leaf-wise absolute continuity, and there is also transverse. Oh, if both of these hold, then it's leaf-wise absolutely continuous. Okay, and this is transverse absolute continuity. It says so this one basically works like this, that suppose this is F, and you have two foliations like this. This is sigma 1, this is sigma 2. These are not foliation, these are, sorry, transversal sections. Sigma 2, and there's a map from here, holonomy map, measurable and bijective, etc. So the measure of sigma 1 is pushed onto the measure of sigma 2. Okay, this is what it means. For our purpose, this is not very important, and this also implies the leafwise absolute continuity. Okay. So now back to our Hoff example. So what happens is, suppose back to maybe on this board, G is the set such that okay, and now we take the case of in the case where we have nice stable and unstable foliation, they intersect and so on, you'll see. So this, and we take a P such that WSP intersection G as full measure in WSP. Okay. Suppose this is P and this is WSP. And we'll, sorry, okay, yeah. So we take a Q here, which belongs to G. Obvious, because this is full measure, okay. And we take WU Q, okay. And we take all such Q. There are, it's almost every Q, like that. And in nice settings, this thing, this union of all these unstable manifolds has to be, say it's G prime, also must have full measure, okay. Then you take G prime intersection G, and G prime intersection G has full measure, done. We constructed a set where this is, what? Yeah, we constructed a set such that phi tilde is constant almost everywhere. Okay, this is just an example. Now we'll explore the phenomenon itself, okay, which is pretty interesting. Now, I will explain the terms after I state the conjecture. Okay. So I need to explain these two terms, partially hyperbolic diffeomorphism and central foliation. So here we go. So this is a generalization of our very familiar notion of hyperbolicity. So what's happening? At every point you have 3 directions. By the way, which board I can reuse? Anyone? Okay. Maybe this one. No. First one. First one. So at every point in the tangent space, there are 3 directions. Not directions, but like splitting. One EU, one EV, one EC. This is P, and this goes to FP. So this EU is preserved to this U, like this U is sent to this EU, this EV is sent to this EV, and EC is sent to EC. And the U direction is expanding, the ES direction is contracting, and EC direction is somewhere in between, okay? Not as contracting as ES, not as expanding as EU, yeah. And by the way, this notion can be generalized. There, you can take more than 3 directions, and you can do something similar. Like the first one is expanding, the last one is contracting, and in between, there, like each one is somewhere in between. It's the definition is not so straightforward, and it's unnecessary. So I'm not quoting it here. Anyway, so it can be shown that the EU direction and the ES direction are both integrable, okay? So at each point you have a stable manifold and an unstable manifold. But the case of the central direction is more complicated. Most of the time it doesn't exist, sometimes it exists but it's not smooth, and so on that in direction. That's why in this conjecture it said that the central foliation, if it exists, okay, because most of the time it doesn't. Now I think now it somewhat makes sense, okay. Generically, what does that mean? So suppose we have a partially hyperbolic diffeomorphism F, which has a central foliation, and we perturb it a little bit in the set of all volume preserving partial hyperbolics. Actually, partial hyperbolicity persists under perturbation, so we don't need to worry about it. So if we perturb it a little bit, we get another foliation. So suppose this had this central foliation like this, and we get what?
What does the central foliation do?
Like, does it expand or does it?
Yeah,
Does it self-intersect?
what leaves?
Yeah. So there are central foliations with circular leaves.
They're invariant too?
Yeah, they're invariant too. So this is the central foliation of F, and we perturb it a little bit in the set of diffeomorphisms, and we get a new central foliation, suppose like this. So the term generic means if this central foliation, the original central foliation, were absolutely continuous, we can perturb it in a way such that it is the resulting central foliation becomes non-absolutely continuous. And if it is, to begin with, a non-absolutely continuous central foliation, then there's a neighborhood where neighborhood of that diffeomorphism where each diffeomorphism has the same property. So basically, in simpler terms, intuitive terms, it is non-absolutely continuous central foliations are much more common than absolute continuous ones. Okay, so this is a very difficult conjecture. It's so difficult that we barely have any idea how to solve it in the general case. Okay, but there are some ideas. Some of them only work for certain cases. Some of them are a little bit general. We have been exploring this conjecture mostly for the case where the manifold has dimension 3, and the reason should be obvious, because for the dimension 3 we can have like EC just one direction, EC one dimensional, EU one dimensional, and ES also one dimensional. So that simplifies life a bit more, a lot more actually. Okay. Now we'll talk a little bit about Lyapunov exponents, which are a great tool in this case and in many other problems, in fact. So it is, the central Lyapunov exponent is defined as lambda Cx. Do you have a question?
Question of Henrique Pujols. Which are the examples now where the central foliation is not AC?
Not what?
Not AC.
Not absolutely continuous. When you have, that's what I was going to talk about. Okay, so whenever you have non-zero Lyapunov exponent, you have that phenomenon. Okay. By the way, WC is the central foliation. Like our notation is this WC. This. So here I've assumed that the central direction EC is one dimensional, but this can be generalized. Okay, so instead of taking just this, we can take one vector, say VC, and we can take this dfn VC, and then we can take the log and the limit, because this value of VC doesn't matter because of the logarithm, it gets cancelled out and stuff. Yeah. So in the general case, there are not just one Lyapunov exponent, there are many, but when you have just one direction, there is just one. Okay. So Lyapunov exponents, the sum of Lyapunov exponents, in fact, has to do with volume. Why? So first of all, we have to think about why do we define something like this? because we want everything to be exponential, even when it's not. Okay, so this construction, limit n goes to infinity, 1 by n log, etc. This has the idea that we want it to be something e power lambda n. Okay, at the limit. Okay, so suppose there are directions, say v1, v2, v3, etc. And you have this direction grows as e power lambda 1n. This direction grows as e power lambda 2n, etc. Then the volume grows. By the way, this is all heuristics. Okay, don't take this too seriously. So the volume grows like this. Product. Okay, so it makes sense to think about the sum of central Lyapunov exponents. Okay. Now, suppose we have compact central leaves. Okay, and we also have the information that the sum of central Lyapunov exponents is non-zero almost everywhere. Okay, or say positive almost everywhere. This doesn't mean the volume expands because see okay, no, just forget about it. Anyway, so we have non-zero Lyapunov exponents, positive Lyapunov exponents everywhere. And we just said that the sum of Lyapunov exponents has to do with volume growth. Okay. So suppose the central foliation is absolutely continuous. Okay. Then we have, it's like this. Take this leaf, say L. And as it's absolutely continuous, at almost every point, the sum of Lyapunov exponents is positive. Okay. Now, that means an expansion of the whole thing. That cannot happen. Okay. So, how can this riddle be solved? This means that the conditional measure which has been induced is not the Lebesgue measure. Okay, it's something like an atomic measure. So actually, at only some points, this measure has this conditional measure has positive has some weight. Okay, and this means the sum of central Lyapunov exponents is positive only at these points. So that paradox doesn't occur. Okay. This is one of the ideas. Like this helps in many cases. Okay. Now, I will tell about some nice results. Three manifolds. So as I just said, this problem is very difficult, and like, we have no idea about how to approach it in the general situation. But we can restrict to, say, 3 manifolds, compact central leaves, and so on. Many more restrictions. So in the case of 3 manifolds, there is a related problem, not related anyway, but it's a problem about partial hyperbolicity, which is the classification problem.
O Henrique perguntou se o exemplo que você mencionou é o Chubby-Wilkinson.
Qual exemplo?
Que você mencionou da pergunta.
Ah, sim. Aqui, ó. Pathological foliation, sim. Mas, cara, esse exemplo é difícil de construir. Porque this example from Shub and Wilkinson is not only non-absolutely continuous, it's pathological. Pathological means absolute continuity fails everywhere. It's also known as Fubini's nightmare. Like on all the leaves, the induced measure is not Lebesgue. And that's, of course, harder example, harder to construct. So, there is also the problem of classification of three manifolds, the classification of partially hyperbolic systems on three manifolds. Like questions like which three manifolds can support a partially hyperbolic diffeomorphism, and what are the ways to find them? Okay. So for quite some time, it was thought that in the case of three manifolds, partially hyperbolic diffeomorphism comes from three sources. Okay, one of them is called dA, derived from Anusov. This was I think the first example was found by Smail. So after it was constructed from a Anusov system by perturbing a little bit a fixed point. Okay, a Anusov system on a torus. Okay, so T3 Anusov system, and perturbing it a little bit, creating a new central direction from that. Okay, so that's one system. And the second system is skew product, which goes like this. So suppose F is M to M is say Anusov, and then you have G a Lie group, and there's a G Lie group, and there's a map theta from F to G. Then the skew product works like this. X comma y is sent to So of course this is a little tricky because we are trying to create a central direction. So we'll have to choose this function in such a way that the rate of contraction or expansion remains between the rates, the contraction rate here and the expansion rate here. Okay. What?
I think the definition of theta is from M to G. Definition of theta.
Yes. Oh, sorry. G's. I'm really sorry. G acts on M. G is a Lie group acting on M.
So I think theta is defined from M to G.
Ah, okay. It's M to G. Yeah. Thank you. Is it correct this time? cross G to M cross G, right? Okay. So one very common thing to do is take an Anosov diffeomorphism on T2 and take the rotation of circle, one rotation of circle, and take a product. Okay, that's one well-known skew product. And there's a third, which is much more straightforward actually. So I have to explain Anosov flow. I won't define, but I'll just say one line about it. It's a continuous version of this. Okay. So it's a flow, and at each point there is a expanding and a contracting direction, and the EC in that case is the direction of the flow. Okay. So as you go along a flow line, one direction gets contracted, the other gets expanded. Okay, that's what happens. And if you discretize this flow, for example, suppose the flow is, say, phi t, and you take phi 1. Okay, you take phi 1. So phi 1 becomes a map from M to M. And then you get back everything from that. Then you get back everything in this definition. Okay. So these are the easiest examples that people used to think that these three may be the only ones, but it has been proved recently that there are many more. So the classification is difficult. But what we can do is we can take some of them, like these three. Okay, we can take them and try to solve this problem in the spatial case of 3-manifold and this kind of diffeomorphism. Okay, and it so happens that this theory is, I won't say it's a theory, but these results are very rich. I think I can erase this now. Okay. Okay. So this result is due to Avila, Viana, and Wilkinson, but this paper is not out yet. So this assumption means basically that the leaves are compact, because 3 manifold. So this this result is very interesting, because the hypothesis is WC exists. As I told you, WC, even when it exists, doesn't have to be smooth. Okay, can be something strange, and if WC is AC, then it's smooth, and then it's it's conjugate to this in the case of rotation, of course. So it's a rigidity result, because we assume only absolute continuity, which is something about measures. It's not a smooth criterion, but we get much more. From a measure theoretic assumption, we get smoothness. Okay, and what is more interesting is, if it's not absolutely continuous, then it fails badly. Like the disintegration of the conditional measures are all atomic measures. As before, as I don't want to use the word conditional measure, I can say something else, like we take a full measure set and it intersects all the leaves, and it intersects each leaf at exactly a finite number of points. Okay. So if it's absolutely continuous, then it's something very nice, it's smooth, and it's conjugate to this. If not, it fails in the worst possible way. Okay, there's nothing in between. And by the way, this result is based on what I said about Lyapunov exponents. Okay, so you have circular leaves. So you can apply that condition that if the central Lyapunov exponent is non-negative, then you have a problem, and then you prove that the phenomenon of having a non-negative Lyapunov exponent is generic, okay, which is the same as saying that the phenomenon of not having absolute continuity is generic. And you can find this result in this paper, which I will cite later. So this result has a second part, which is more interesting, which is theorem 2. This is closed. similarity between the two results should be evident. Okay. This result is also due to Avila-Viana-Wilkinson, but this one is publicly available. So what's the idea? S is a closed negatively curved surface, and we are talking about its geodesic flow. It's a celebrated result of Anosov that this geodesic flow is an Anosov flow. Okay. So this means the time one map of this flow gives a partially hyperbolic diffeomorphism. Okay. And we also have M is preserved by phi t, and we have a neighborhood U of phi 1. Phi 1 is a time one map, which is C1 open in this set, which is the set of all M preserving diffeomorphisms of the unit tangent bundle of S, such that for every F in U, either this happens, the first option, which is, as I said multiple times, is the case of atomic disintegration, and the second case is a set of Lebesgue disintegration. Okay. But this result again is very interesting because it just the fact if like just absolute continuity or the lack of it implies something very strong. Like it's a time one map of a C infinity flow preserving M, which is a smooth phenomenon. So from measure theoretic information, we go to the domain of smooth things. And again, like if absolute continuity fails, then it fails in the worst possible way. The first point, atomic disintegration. Okay, maybe we can stop now.
This is in all of U. It's not just a generic phenomena, just in all of the open set U.
Yes, yes.
But there was another question. Can I? I have no idea. I'm just learning these things right now.
Okay.
But there are some new examples of partial hyperbolic maps.
Yeah, there are some new examples, like apart from these three, yeah.
And Bonatti.
Yes, Potri. I don't know if I'm pronouncing correctly. Potri.
I think
Uruguay.
It's okay. Yes.
And Bonatti, etc. Yes, there are. So, by the way, I didn't.
Do you know what happens about then? Can you say anything about that?
Yeah, that's what I'm trying to do right now. In fact, yes, like maybe in a few months I will have an answer.
You have not just a simple, very, very heuristic idea of what they are?
No, because the thing is, these examples are relatively simple. Their examples are like really complicated. They apply surgeries and stuff. But their examples have some compact leaves sometimes. So maybe there can be some hope there, don't know.
Any more questions?